Optical fiber. Optical fibers are constructed with a cylindrical core surrounded by a sheath of cladding material. Common materials used are pure silica N2 equals 1.45 for the cladding and silica doped with germanium N1 equals 1.465 for the core. Part A. What is the critical angle theta critical for light traveling in the core and reflecting at the interface with the cladding material? So this is the core, this is the cladding material. So this reflection is what we're talking about. So you want to find the critical angle for the total internal reflection at this interface. So for total internal reflection, if I draw the normal to the surface, this is the incidence angle theta 1 and this is the angle with which it refracts, theta 2. And now if I have total internal reflection, if I write Snell's law, N1, the interface, the medium where the light is incident on the interface is N1, index of refraction, sine theta critical must be equal to N2 sine 90 degrees. So at this interface, there will be no refraction. So theta 1 is my critical angle now, and theta 2, the angle with the normal, is 90 degrees on the second medium. So this tells me that the critical angle, theta critical, must be equal to, because sine 90 is 1, sine inverse N2 divided by N1. So for the given values here, this is the critical angle. Now for the given values, this is equal to sine inverse N2 is 1.45 and 1 is 1.465. So N2, the index of refraction of the cladding material, and N1, the core material. This gives me a critical angle, theta critical, 81.8 degrees. Now moving on to part B, the numerical aperture NA is defined as the angle of incidence theta I at the flat end of the cable, so this angle, for which light is incident on the core cladding interface at angle theta critical. So theta 1 is theta critical. Show that sine theta I, sine of the numerical aperture, is square root of N1 square minus N2 square. Okay, so we're also talking about this interface now. The light comes from air with the angle of incidence theta I, and it refracts with angle alpha here, and here we have a right triangle. So this is 90 degrees. So using Snell's law at the fixed flat end, the index of refraction in air is 1, sine theta I, the numerical aperture. This is equal to N1 sine alpha. So what I have done is I have written Snell's law at the flat end. Now for the core cladding material interface, we have N1 sine theta critical is equal to N2 sine 90. which is what we have used in part A. And we also know from this right triangle that theta 1 is 90 minus alpha. So the critical angle, theta critical, is 90 degrees minus the angle alpha. So this equation, n1 sine theta critical is n2 sine 90, is Snell's law at the core cladding interface. So looking at this equation, n1 sine theta critical is equal to n2 sine 90, and noting that theta critical is 90 minus alpha, this equation basically says n1 sine 90 minus alpha, which is n1 cosine alpha, is equal to n2. Okay, so we have sine alpha and cosine alpha here. So we know that sine square alpha plus cosine square alpha is equal to 1. Now what is sine alpha? Sine alpha is sine theta I, the numerical aperture, divided by n1. So this is going to be sine square theta incidence divided by n1 square. What is cosine alpha? Cosine alpha is n2 divided by n1. So this is n2 square over n1 square. This must be equal to 1. So n2 square plus sine square theta incidence is equal to n1 square. In other words, we can write sine square theta incidence is equal to n1 square minus n2 square, or this can be written as sine theta incidence numerical aperture is n1 square minus n2 square square root. So let's check if this is what we were supposed to show. Indeed, this was the equation we were supposed to get to. Now part C, what is the value of the numerical aperture for n1 equals 1.465 and n2 equals 1.450? Well, we can use this equation. And now the numerical aperture is equal to sine inverse 1.465 square minus 1.45 square square root and this gives us an angle of incidence 12.1 degrees. That's the numerical aperture. Okay, so in this problem we're talking about an optical fiber. We have light incident from the flat end. It refracts at the air core interface. It enters the core and then it's going to go through total internal reflection at the core cladding interface. So light will travel throughout this fiber without entering the cladding material. So it will be transmitted to the other end of the optical fiber. Now the pure silica n2 equals 1.450 is the cladding material, and silica doped with germanium n1 equals 1.465 is the core material. So first we were asked to find the critical angle for the light traveling in the core and reflecting at the interface with the cladding material. And that is the angle with the normal here, theta 1, the critical angle. For total internal reflection, we must have n1 sine theta incident is equal to n2 sine 90, so that there is no refraction. And this gives us the critical angle sine inverse n2 over n1, 81.8 degrees. And then in part B, we were told that the angle of incidence is called the numerical aperture at the flat end of the cable. And we were asked to show that sine of the numerical aperture is square root n1 square minus n2 square. Well, applying Snell's law at the flat end, the index of refraction of air 1 times sine theta incidence is equal to n1 sine alpha when it enters the core material. So this tells us that sine alpha is sine theta incidence over n1. And at the same time, for this critical angle theta 1 here, and 1 sine theta critical equals n2 sine 90, we see from this right triangle that theta 1 is 90 minus alpha. So n1 sine 90 minus alpha is actually n1 cosine alpha, which is equal to n2 because sine 90 is 1. So cosine alpha is n1 over n2 over n1. So sine square theta I over n1 square, sine square alpha, plus n2 square over n1 square, cosine square alpha equals 1. This gives us the equation sine theta I is equal to square root of n1 square minus n2 square. If we substitute the numerical values given in the problem, we find that the numerical aperture should be 12.1 degrees.